Good morning. I'm here to present the work done by my research group at California Polytechnic State University on distributed non-negative matrix factorization simulation simulated in Golang. Sorry. These are the name of my group: Keen Coleman, Ryan Nett, and Nick Shore. Okay, so non-negative matrix factorization is an algorithm used in machine learning where an input matrix A is actually subdivided in two low-rank matrices, W and H, so that A is equal to W and H, W multiplied by H, sorry. Because there is no general solution to this problem, then most algorithms, what they do is an approximation to this problem. So they provide an approximation, not a generic solution. The algorithm is used in audio, text mining, clustering, for image and video compression and so on. So it's very frequently used. It is a learning algorithm, so it's implemented, most of the implementations use an iterative approximation and those kind of algorithms, learning algorithms through iterative approximation, they are actually slow. So that's why we actually propose this work. We distribute the non-negative matrix. We distribute the non-negative matrix factorization algorithm. And because there are actually many different solutions to this problem, and some of them are easier and more, or some of them are more difficult to actually implement as a distributed system, we are actually, we chose to implement the one that is actually based on multiplicative updates, and it calculates the convergence through the Kullback-Leibler divergence. We also we were looking for different implementations of the non-negative factorization algorithm, and we found that the only one that we found is this one, MPI FAUN, and it uses message MPI, obviously, as the programming language to distribute the algorithm. And the thing is that MPI is all over the place on high performance computing cluster, right? They have no problem in running this kind of algorithm, MPI-based algorithm. But the smaller research institution and the smaller universities, it's very rarely they will have an MPI cluster. So that's the reason why we decided to change this implementation from MPI into Go routines. Go routines, Go programming language is becoming very frequently used in server-side programming, and it's very easy. It was written so it's easier to distribute and write distributed and concurrence application, right? And because it has very low overhead in the system stack, so we decided to implement our own algorithm for non-negative matrix factorization, but to do it in Go routines. Now, to make sure our algorithm provided the correct implementation, or it was equivalent to the MPA FAUN, then we actually ran all the benchmarks that MPI has. We actually run it on our implementation to make sure that we are equivalent to them. A little bit more about the non-negative matrix factorization, and the NMF is using machine learning, the most use for machine learning is because there are different implementations, and some of them are actually older, but mostly all of them are from around the 90s. But the one that everybody's using in machine learning is this one from Lee and Seung from 1999. And it's similar, and the applications that they wanted to use it for was similar to a principal component analysis or the singular value decomposition. One particular thing about the non-negative matrix factorization is that whatever the matrix W and H, we find the values for the matrix and the elements on the matrix cannot be negative. So it's easier to do operations on them. But that's actually a very important quality of this algorithm. The composition of A into W and H, because we can actually decompose it in different matrices. So we have to choose the rows and columns for each one of them. And this rank that we choose for the decomposition determines what the approximations will be. This rank is a unique basis vector that you need to actually generate the matrix, and usually they have to be bigger than the A, the M, and the number of rows, number of columns on matrix A, in order for the results to make sense. So they are useful, not to make sense, but the results to be useful. We have in here the entire code, so you can replicate our work. And if you need an implementation, an acceleration of this algorithm, then you are more than welcome to use it. You can find it here at this GitHub link. This is actually the non-sequential implementation. This is the sequential implementation of the algorithm. It's based on the divergence. So this is the Kullback, I always mispronounce it, it's the KL, but it's the Kullback-Leiber divergence, is to measure the divergence between two distributions. So in this case, it's transformed, so it can actually measure the divergence into matrix A and the result matrix of W multiplied by H. So this is how we are going to measure the divergence between the two matrices, and the goal is to actually minimize this value. So the sequential algorithm is relatively simple, and you initialize the variables, the matrix W and H to random values, and then there is a for loop that says that while we didn't meet the convergence goal, and we set that convergence goal, then we update W with a fixed matrix multivariate factorization of H, and we actually update H also with a fixed value for W, like this, like the formula is here. And once we are satisfied with the convergence, then we actually return the value of W and H. This is our parallelization. So we want to describe, because the main contribution is actually the parallelization, right? So we have an initial matrix A, and we divide it in chunks, different chunks, and the number of chunks, it depends, is actually, we decide. It can be the number of nodes that we have on the cluster, or the number of cores that we actually have on one individual machine. But for example, we divide the initial matrix in six chunks, and then we initialize the W and H with values, but then we also divided in the chunks by rows, chunks by columns, and the colors actually means what each node in the cluster or thread in the, if instead of a cluster is just one individual machine, Go routines will also go and distribute through the cores. So Go, the benefit of Go is that if you only have one machine, it will distribute through the cores of the machine. If you actually have a cluster of different computers connected together, then it will actually distribute through the different nodes, right? So the colors, the same colors means that this is the information that each one of the nodes needs to calculate their own chunk. And then because it's Go routines, then we have channels, we create channels to communicate among the Go routines, so they can actually pass their results, and they can also have access to their arrays, the local arrays that they are actually manipulating. So we have two channels per Go routine, one to actually send the input data around, just in case they need some communication on the border, but they actually can communicate the input data, send the chunks, and so on, and then another one to actually create the results. A little bit more about that. So this is the diagram of how the data is actually divided. This is actually how the algorithm is divided. And we have marked every important distributed or parallel distributed function that can actually be done by the entire cluster. We mark it with this: all reduce, all gather. So all the nodes reduce, all the nodes gather, reduce, gather, and so on. Very similar. We give the same names as MPI does, but we actually had to implement this all reduce in Go. By doing communications, Go, the communication channels in Go are just, if you have any question, you can ask me at the end of the presentation, but the communication channels are similar to pipes in operating system, similar. But for example, this, because if you see, this is a summation of all the elements in U, so that is a reduction operation, and all the nodes can actually do the reduction operation. So I send my value to the node that is next to me, and he's the one adding. So we are doing the reduction also as a tree reduction. And the same with the scatter and gather and so on. So we mark the algorithm with all this information, so you see that this can actually be, it is being done in parallel. We tested with different, like I said, we tested with the test bench that MPI FAUN uses, and it has small matrices like this one, but then it has bigger, much bigger matrices. So the results that are being produced are exactly the same. So we are competitive. You can choose to use our algorithm or the MPI. The results are going to be the same. For a small size arrays, the timing were exactly the same also. But right now the situation is that when the arrays are much bigger, then our Go routine implementation takes 3 minutes. The MPI implementation takes 56. So we are slower than MPI. The reason that we are still working on optimization on the communication, and not only on the Go routines, how the Go routines communicate, that's programming, but we are also optimizing our cluster. We really don't have a cluster. We only have the lab computers, and we use and Go. Go is able to send through HTTP messages. So we use that to distribute the messages and the chunks of the array. But if we actually had a more dedicated cluster like the MPI, an MPI cluster that the communication is very specifically done, we think we will be also competitive. Still working on it, but the timing, the implementation is, I mean, the results are fine. We are competitive with MPI. I want to make sure that at the end I don't leave with like, oh, they weren't able to do it. We are comparing ourselves. We are much faster than the sequential implementation, but MPI is not sequential. MPI is a distributed, and MPI has been optimized for already more than 20 years, right? So that's why we wanted to make sure the algorithm is correct. Now we are going to make sure that the communication is also correct. And we mainly are working now on the networking side, not so much on the software, which is what I'm presenting here. Okay, so I'm out of time. Thank you. Hope to see you soon.